Good evening, everyone. I hope I'm audible. Can someone confirm?
Yes, sir.
Okay. So today we will be discussing problems from the week 8, that is the negative feedback of op-amps and circuits related to negative feedbacks of op-amps. And yeah, as these are interactive sessions, I will expect you to solve the questions along with the session. So let's start with the first question. So in this question, you need to find out the input to output voltage for the given circuit. So you need to find out the gain for the given circuit. And the op-amp over here is a non-ideal op-amp. That means its gain is not infinity. So please try it out. Okay, so let's see the solution for this. So first of all, we know that the op-amps have a high input impedance. So they are ideally infinite, and since nothing is mentioned in the question, so we will assume that that part of the op-amp is ideal. So in that case, any current won't flow inside the terminals of the op-amp. So there won't be any voltage developed across this 2 kilo ohm resistor. So this 2 kilo ohm resistor can be neglected. And if we do so, so we have a unity follower with where the ideal gain should have been 1. Now, like in the circuits with negative feedback, what you have is like the gain, the actual gain with non-infinite open loop gain. This is the formula for that. That is, whatever the ideal gain is there, that is multiplied by the loop gain upon 1 plus loop gain. And open loop gain in this case, as this is unity feedback. So you have this. So to find the open loop gain, you cut the loop at the output. And if you find the gain from VT to V out, the gain is basically, this is the open loop gain, and this is minus of A naught. So, and in the question, A naught is given as 999. So, the in ideal case, the gain would have been 1. So, V out to V in is 1 into A naught upon A naught plus 1, that is 999 upon 1000, that is 0.999. So, if you want to solve it in a traditional way, so from where we get this formula. So since this is a short circuit from negative feedback, negative terminal of the op-amp to the output. So the output and negative terminal both are V naught. So you have V in minus V naught times A is again equal to V naught. So if you rearrange it, you get the same expression of V out to V in, that is A naught upon A naught plus 1. Any doubt in this?
No, sir.
Okay, so let's move to the next question. So in this question, so you have both negative as well as you have the feedback both on the negative terminal and the positive terminal. However, you need to find the condition on R and a condition between R and RA so that the overall op amp remains in negative feedback. Please try it out. Okay, so those who have joined right now, we are solving questions on week 8 uh, concepts, that is negative feedback in the op amp and circuits related to them. And this is the second question. So here what you need to find is, so you have a circuit in which you have both positive as well as negative feedback, and you need to find the relation between R and RA so that the overall op amp remains in negative feedback. So please try it out. Okay, so let's see the solution for this. So first of all, like these inputs are given. Now for any loop gain calculations in which you need to find the loop gain of the op amp, the closed loop, open loop gain of the op amp, or the stability of the circuit, which you will get familiar with in later weeks. So in these cases, the input that you apply doesn't matter. So these inputs can be shorted. So if you short these over here, now you have this particular circuit. Now, what you need to do, you need to find the loop gain from V test to V out. So if you have a voltage V test over here and these are shorted, so at these points you can apply a resistor divider between RA and R and 2R and R to find out the voltages at these nodes. Now, once you find the voltages at these nodes, so V positive minus V negative times A is equal to V naught. So A times Vt times Ra upon Ra plus R minus 2 by 3 is V naught. And so for this complete op amp to be negative feedback, the loop gain has to be negative. So V naught by Vt has to be negative. So Ra upon Ra plus R minus 2 by 3 must be less than 0. So from there you get Ra must be less than 2R for as the condition for this circuit to be negative feedback. So one thing that you must always remember is like in any general circuit, the gain from the test voltage to the positive terminal should always be lesser than the gain from test voltage to the negative terminal for the op amp to be in negative feedback. Any doubt in this? Okay, so let's move to the next question. So now in this question, so you have a op amp and you have three switches over here, namely A2, A1, and A0. And the function of the switches is that if A1 equal to 1, then this will be connected like this. And if this particular thing is equal to 0, then this will be connected to ground so that no current from this flows into this. Okay, so when it is 1, the current that is flowing will flow like this. And when it is 0, the current will flow in this direction. So same is the case with A2, A1, and A0. So what you need to find is the output voltage V0. So when A2, A1, A0 is 1, 0, 1 respectively. So please try it out. And V0 is the output voltage over here. So let's see the solution for this. Now, here is the circuit. So if you consider only the network on the negative terminal of this op amp, so you have it like this. So you have a reference voltage of 5 volts, and that supplies current to this network, and the terminals of these 4 kilo ohm resistors are A1, A2, and A0. So now one thing that you should observe is that whether the A2 is connected to whether either of these switches are connected to ground or virtual ground. In both the cases, the voltage at these terminals will be zero. So, uh, like as far as this this whole network is concerned, that won't change irrespective of the switch, the position of the switch. So, uh, having said that, we can find out the values of these currents. So, if we try to do that, so what we get is, so we can replace A1, A2, A3 by grounds, because either it is actual ground or virtual ground. This network will not be affected. So we have 2 kilo ohms looking in from here, then 2 plus 2, 4 kilo ohms, then again 4 kilo ohms, 4 kilo ohms in parallel. So the series keeps on repeating. So you have 2 kilo ohms that this 5-volt voltage source is seeing. So the current I that flows is 2.5 milliamps. And now, since this voltage is 4 kilo ohm, this voltage is 4 kilo ohm, so current will be divided by 2 in these two resistors. So it will be 2.5. So I1 basically will be 2.5 by 2 milliamps, and similarly will be the current that is flowing in this 2 kilo ohm branch. And again, this 2.5 by 2 milliamps will again divide into halves, and hence I2 will be 2.5 by 4, and similarly I3 will be 2.5 by 8 milliamps. Now, if you have, let's say we denote these variables A1, A2, A3. When A1 is 1, that means it is connected to virtual ground, and when A1 is 0, that means it's connected to the other ground, that is no current is flowing into the op amp. So in this case, what you can write as the overall output voltage is, so this is the I1 flowing, and here you have A1. This is the I2 flowing, and here you have A2. Similarly, this is I3, and here you have, sorry, okay, okay, sorry, I2, I1, I0. This was the nomenclature that I used earlier. Let's stick to that. A2, A1, A0. So all these currents will flow through the op amp, and as you can see, this is a 3 kilo ohm resistor through which these uh, currents go. So you have the voltage that will be developed at the output will be the overall current multiplied by this 3 kilo ohm resistor and its negative. So this voltage is zero. So whatever current flows through this, that will develop a negative potential at the output. So if you see that, so if A2 is 0, then the current I2, that is 2.5 by 2, will flow inside the 3 kilo ohm resistor, and it will develop a voltage of 2.5 by 2 times 3. Sorry, if A2 is 1. So this will develop this voltage. Similarly, with the case of A1 and A0. So if you see this expression, you take 2.5 by 8. If you take out common, so what you have over here is 7.5 by 8 into this thing. Now, this, if you remember your binary to decimal conversions, so this is the same thing. So if you have some binary bits as A0, A1, A2, where A2 is the most significant bit. So to convert it into decimals, what you do is you keep on multiplying the power of 2 with respect to whatever position that bit is in. So here, this is a binary to a decimal conversion that the circuit is performing, and the circuit is known as a DAC. So this is a R to R DAC. So Have you guys studied about it till now? So, if you have not, then you will probably study it in later advanced courses. So, this is a digital to analog converter. So, it converts the digital bits that are A2, A1, and A0 into some analog output voltage, that is V0. So, the code that so you can plot it like this. So, on x-axis, I'm plotting the codes that is A2, A1, and A2, A1, and A0 respectively, the values of this. And on y-axis, I'm plotting the normalized output voltage 8 by 7.5 times V0. So if you see that all the bits are zero, the output voltage is zero. So if like the least significant bit is on, the output voltage will be 1 times 7.5 by 8 and so on. So it will go till 7. So the range of this is from 0 to 7 into 7.5 by 8. So this DAC will give you an voltage from 0 to this value depending on whatever bit sequence you have. Any doubt in this? Okay, so let's move forward. So in this circuit, you need to find the current I for that this op amp will provide for the given setup. And the input is a 2 milliamp ideal current source. Please try it out. Okay, so let's see the solution for this. So what we will have is, first of all, since this op amp is a negative feedback, so virtual ground will be there. So since this is at 0 volts, so the negative terminal will also be at 0 volts. Now, this current will flow, this 2 milliamp current will flow, and anything in series with ideal current source is redundant. So this 2 kilo ohm resistor doesn't has any significance over here. And since the input resistance of this op amp is infinite, so current flowing in this direction will be zero. So all this 2 milliamp will flow through this 2 kilo ohm resistor, and that will develop a voltage of 4 volts across this. And since this is 0 volt, this is 4 volt voltage is developed across 2 kilo ohms. So the output voltage will be minus 4 volts. And this minus 4 volt will create a current of 1 milliamp through this 4 kilo ohm resistor. So this 2 milliamp and 1 milliamp both will flow inside the op amp, and the total voltage that total current that will be flowing, the I is basically minus 3 milliamp. So, like in general, any circuit, if the op amp is ideal, all the currents that are flowing through this terminal. So basically, the ideal op amps drive whatever load is presented to it. So had there been this, instead of this 4 kilo ohm resistor, there had been some, maybe let's say 10 kilo ohm resistor, the output voltage wouldn't have changed. Only what would have happened is the amount of current that this op amp has to supply or sink in would have changed. So this is how circuit with negative feedback of op amp works. Basically, their output resistance is zero. Any doubt in this? Okay, so let's move forward. Now in this question, you have a non-ideal op-amp that is connected into non-inverting feedback configuration. What you need to do is you need to find the gain of this op-amp such that 100 times the ideal gain from input to output minus the real gain from input to output is less than 1%. So yeah, for that you need to find out the gain. Please try it out.
Good afternoon, sir.
Sorry, Dheeraj, do you have any query? Okay, let's so let's see the solution for this. So first of all, like had this gain been infinite, there had been virtual ground, the perfect virtual ground. So this voltage will be equal to Vi. And since this is a non-inverting configuration, the gain that will be there from input to output will be RF by R1 plus 1, where RF is equal to 9 kilo ohm and R1 is 1 kilo ohm. So the ideal gain that you get is 10. Now, in the real scenario, what will happen is if this voltage is out, this voltage is V out. So by resistor divider from V out to the negative terminal will be the negative terminals voltage can be calculated. So that will be V naught into 1 kilo ohm by 1 kilo ohm plus 9 kilo ohm. So it will be this will be equal to V naught upon 10. So what will happen is again this positive terminal minus negative terminal times A is the output voltage. So V out is equal to A times the voltage at positive terminal, that is Vi, minus the voltage at negative terminal, that is V naught by 10. So from there, if you try to try to simplify this uh, particular equation, you can arrive to this kind of expression, that is V naught by Vi is equal to 10 times A by 10 divided by 1 plus A by 10. So as I mentioned in one of the previous questions that any non-ideal circuit with op-amps with non-infinite gains, how you need to find the non-ideal transfer function is that the transfer function that in ideal case into loop gain upon 1 plus loop gain. So here if you try to find out what is the loop gain, so for loop gain calculations, as I mentioned previously, you need to break the loop at the output, and if you apply the test voltage over here, So let's call this VT and let's call this VA. So from VT, if the voltage at this node will be when once you are while you are calculating the open loop parameter, so for that you can ground this input terminal. So from VT to the negative terminal of op amp, you have VT upon 1 up by 10, that is through resistor divider, and then this get multiplied by the gain of the op amp. So VA is basically equal to A by 10 into VT, minus of A by 10 into VT. So this is the loop gain. So and
Sir,
yeah, Dheeraj, do you have any query? Okay, so the A by 10 is the loop gain, and
understanding me, sir.
yeah, Dheeraj, do you want to ask something? Hello. So your voice is unclear. If you have some query,
Sir,
please
not
type it
understand
out
this.
in the chat window. Your voice is unclear. Please type it out in chat window. Can you do that? Okay, so Dheeraj, please type your I can't really decipher what you are saying. I think there is some network issue on your side. So whatever doubt you have, please type it out in chat window. Okay, so uh, anyways, okay, I will explain this question once more if you were not able to understand it. So, okay, so let's start it from the beginning then. So what we have over here is we have a non-ideal op amp that is connected in non-inverting configuration, and these are the this is the complete circuit. Okay, so in the question, what is asked is that you need to what will be the A so that the 100 times the ideal gain, uh, 100 times ideal minus V naught by Vi real is less than 1. So this was the question. So for that, basically what you need to do is first of all find, the ideal gain will be the gain of non-inverting amplifier, that is 9 kilo ohm by 1 kilo ohm plus 1, that is equal to 10. And the real gain will be a real gain you need to find out. So the traditional way I showed you over here. So from there you get 10 times A naught by 10 divided by 1 plus A naught by 10. And what I was explaining was that like in any such circuit where the gain of the op amp is non-infinite, so in this case, what you will do is the gain from output to input, the real gain will be the gain that is the ideal one multiplied by loop gain upon 1 plus loop gain, where loop gain is the modulus of basically loop gain is the modulus of the gain, the open loop transfer function from of this op amp. Okay, so H of S, let's call it H of S. Now to find the open loop transfer function, what you need to do is, first of all, you need to de-energize all the input sources and then break a loop at a suitable point. So for this question, I'm breaking it at the output of the op-amp and then find the open loop gain. So if you do that in this question, what you will have is, you will have, let's say you apply some test voltage over here. You have 9 kilo ohm resistor in the feedback path, and then you have a 1 kilo ohm resistor over here. And this, since the input voltage source is de-energized, is zero. So if this is Vt, this voltage will be the resistor divider, that is Vt into 1 divided by 9 plus 1. That is equal to Vt by 10. And hence the output voltage will be, the Va will be minus of A times Vt by 10. So loop gain over here is A by 10. So what is the transfer function from input to output? That is the ideal transfer function, that is 10 times A by 10 upon 1 plus A by 10. So this is similar to this is exactly same as what you got through rigorous calculations. So this thing you can use it as a quick to find the transfer functions quickly. So now once you have this real transfer function, so from there you can find out. So once you have this real transfer function, so the percentage error in terms of the gain of the op-amp can be written as this. So it's 100 times the ideal gain divided by 1 plus A by 10. That is the loop gain. So on simplifying it, you get A as 9,990. Any doubt in this? Okay, so let's move to next question. So in this question, again, you have circuit. So first of all, can you guys please, can anyone point out whether this circuit is in negative feedback or not? So we have solved such example previously. So uh, based on that concept, can anyone point out that if the circuit is in negative feedback or not, and if yes, then how? Okay, so again, to find the sign of the feedback, you have to see. So as I mentioned earlier, that gain from output to the negative terminal of the op-amp shall be higher than what you have from output to the positive terminal of the op-amp. So if you uh, try to check this, so first of all, for that you have to de-energize the input voltage source. So from there you get this gain is so this voltage is basically 4 divided by 4 plus 20, that is equal to 1 by 6, and this voltage is 8 divided by 20 plus 8, that is equal to 2 by 7. So out of 2 by 7 and 1 by 6, which one is larger? So naturally 2 by 7 is larger. So since the gain from output to the negative terminal of the op-amp is higher, so this op-amp, yes, this op-amp is a negative feedback. Now, once you have figured this out, then you know that the virtual ground voltages are virtual ground is valid, and the positive and negative terminals of the op-amp are equal. So in this case, now please try to find out the gain from output to input. Gain from, please try to find out the current that this voltage source is supplying. Sorry for the inconvenience. Okay, so now to solve this question, that is to find out the current that this 1 volt voltage source is supplying. So what you need to do is you need so with this input voltage source intact, you need to find the voltages at these two terminals. So for negative terminal, it will be the resistor divider from V naught to this point, that is 2 by 7 times V naught. And this Vx can be found out by superposition. That is, once you have only V naught and ground the other terminal, that is this 1 volt. So from there you get V naught by 6. And then in the other case, you set V naught as 0 and find out the voltage due to this input voltage, that is 1 volt. So that is 5 by 6 times Vi, and Vi in this case is 1 volt. So then equating the voltages at positive and negative terminal, you get V naught by Vi as 7. And from there, you can get the voltage at now, since you have the V naught in terms of Vi, so you can substitute this in this equation, that is the voltage at Vx, the positive terminal. From there you get voltage at Vx as 2 Vi, and the current then will be current I will be Vi minus Vx by 4 kilo ohms. So if you substitute it, you get the current as minus 2.5 milliamps. Now, you should note in this case is that since the current is in negative direction, so this current is basically flowing inside the positive terminal of this 1 volt voltage source. So even after being a active element, this voltage source is not actually supplying the power; it is dissipating the power. Now, in this complete circuit, can anyone tell which element is actually supplying the power? Because you know that the power cannot be created or destroyed. The power has to be conserved. So if so, you know that these resistors are passive, so they cannot supply the power. And since you have calculated the current and that is flowing inside the positive terminal of this voltage source, so this also cannot supply the power. So which element is supplying the power? Can you guys tell? So in this case, basically this op amp is supplying the power. So this op amp is a active element. So in any amplifier that consisting of an op amp, the op amp's job is to supply whatever power difference is there between input and output. Any doubt in this? Okay, so let's move forward. So now in this circuit, you need to find out the gain from input to output terminal. So let's see the solution for this. Now again, this circuit is in negative feedback because there is only one feedback path, and that is from output to the negative terminal of the op-amp. So now since it is a negative feedback, so virtual ground will be valid, and since positive terminal is at 0 volts, the negative terminal will also be at 0 volts. Now this 1.2 kilo ohm resistor, since has no voltage difference across it, so Ix will be equal to 0. So and now for this 1.2 kilo ohm and 1.2 kilo ohm, the one terminal is common, and the other terminal, both of them are at 0 volts. So looking in resistance from here will be basically 1.2 kilo ohm, 1.2 kilo ohm in parallel. So that will be zero point 0.6 kilo ohms. Now 1.2 kilo ohm and zero point 0.6 kilo ohm in series. So I1 will basically be equal to VI upon 1.8 kilo ohms. Now, this I1 will be divided equally in 1.2 kilo ohm and 1.2 kilo ohm resistor. So I2 basically will be equal to I1 by 2, that is VI by 3.6 kilo ohms. And since no voltage, no current Ix flowing is 0, so all the current, this I2 will flow through this 4.8 kilo ohm resistor, and hence the voltage developed across this resistor will be the negative of the output voltage. So what you will have as output is 4 point minus of Vi upon 3.6 times 4.8. So this comes out to be minus 4 by 3. It is minus 1.33 times Vi. So the gain is minus 1.33. Any doubt in this? Okay, so let's move to the next question. So here, find out two things. One is the input resistance that is being seen with by this uh, voltage source Vi, and the other thing is the gain from output to input. Sorry, input to output. This gain you need to find. So please try it out. Okay, so let's see the solution for this. So again, since there is only one feedback path, and that is from output to the negative terminal, so this op amp is in negative feedback. So virtual ground is valid, and if the virtual ground is valid, since the positive terminal is at 0 volts, so a negative terminal will also be at 0 volt. So this 2.4 kilo ohm resistor will be redundant. So the current that will be flowing through this 5 kilo ohm resistor will be Vi minus 0 by 5 kilo ohms, and hence the equivalent resistance that this voltage source will be seeing will be 5 kilo ohms only. So now to find out the gain from output, from input to output. So first of all, we can equate the voltages with respect to input and with respect to output at this terminal, this node. So with respect to output, this voltage can be found out by this network. So what you have over here is this 2 kilo ohm goes to the virtual ground, and this 5 kilo ohm is at the actual ground. and then you have a 3 kilo ohm resistor over here, and here you have output. So this 2 kilo ohm, 5 kilo ohm are in parallel. So resistor divider at this will be 2 parallel 5 divided by 3 plus 2 parallel 5. So this gives you 10 by 31. And from input side, if you check, so this voltage is 0 volt, and the input current that is flowing is VI by 5 kilo ohms. So, and that current develops a voltage across this 2 kilo ohm resistor. So from input side, you have minus 2 by 5 times VI. So if you equate these two, from there you get the gain as minus of 1.24. Any doubt in this? Okay, so let's move forward. Now, in this question, again, this is a similar question as we discussed previously. So, we need to find, so here the gain of the op amp is already given. And given this gain of the op amp and this circuit, we need to find out the the percentage error between the ideal gain and the real gain. So, please try it out. Okay, so let's see the solution for this. So, as we discussed earlier, we can find out the real transfer function as a naught into, the loop gain over here will be this resistor divider multiplied by this gain of the op amp. So it will be a naught into 1 kilo ohm divided by 1 plus 3 kilo ohms. So that is equal to, so the loop gain is a naught by 4. So, and the ideal transfer function, since this is a non-inverting configuration, so V naught by Vi ideal will be equal to 1 plus 3 by 1, that is equal to 4. So, the real transfer function will be 4 times A naught by 4 divided by 1 plus A naught by 4. So, if you plug it in the definition of the error that is mentioned in the question, so the error you will get is 100 times 4 minus 4 into A naught by 4 divided by 1 plus A naught by 4. So on simplifying this, you get a percentage error of 4%. Any doubt in this? Okay, so let's move to the next question. So in this question, there is slight modification in the from the previous question only. So earlier you had only so this circuit was not present. So between the output of op amp and output of the actual circuit, an additional circuit has been placed. And in this case, again, you have to find out the percentage error from V out, from V in to V out. So you first of all find out the ideal uh, gain and then the real gain. Okay, so let's look at the problem. So if you closely look at it, only the gain from this part to this part, how you can find it? So the real gain will be so from here to here, it is again a non-inverting op-amp, op-amp in non-inverting terminal. So gain will be 1 divided by 1 plus 1, that is 2, and the loop gain will be this a naught. The resistor divider from this point to this point is 1 by 2, and the loop gain is a naught by 2. So overall gain from this point to this point is 2 times a naught by 2 upon 1 plus a naught by 2. So if you plug the value of a naught in this equation, you get the gain as 1.99. Now, if you look at this complete circuit, so what you have is an op-amp, and in cascade to that, another amplifier that gives you a gain of 1.99. So you can consider this complete circuit as one op-amp that has got a gain of A naught multiplied by 1.99. So that comes out to be 788.02. So the error that is there, so earlier you had, in this case you had A naught, now you have it as A1. So error you have is of 2 now. In Previously you had an error of 4. So what you see is, when you try to cascade multiple stages with gain greater than 1, you reduce the overall error in the transfer function. Any doubt in this? Okay, so let's move forward. Now, in this question, again, this is a similar kind of question. So that this concept we have visited multiple times in this session. So you need to find out the signs of these A and B terminals, so that this complete op amp is in a negative feedback. So for this, what you will have to do is this again, from output to terminal A and terminal B, if you try to calculate the gains. So for terminal A, it's 2 by 8 times V naught, that is V naught by 4, and terminal B, it's V naught by 5. And the one that has got higher gain should be the negative terminal, so that the overall op amp is in negative feedback. And since V naught by 4 is higher than V naught by 5, so negative terminal should be A. And the B uh, conclusively will be positive terminal. Any doubt in this? Okay, so let's move to the final question. So in this case, again, you need to find out the gains of A and B, the signs of A and B for both the op amps, and then it is mentioned that for these two voltage sources, the output is a linear combination of these two voltage sources, and these coefficients of these voltage sources is alpha and beta. So you need to find alpha and beta. Please write out. Okay, so let's see the solution for this. Now, How you need to, so for the sign of the op-amps, first of all, let's consider the sign of op-amp 1. So in op-amp 1, you break the loop at the output of the op-amp 1. So from V1 to the out, so now this complete circuit is a negative inverting amplifier configuration. So gain from V1 to the output of this op-amp 2 will be a negative gain, and its value will be minus 8 by 2 kilo ohms, that is minus 4. And then you have a resistor divider that will that won't change the sign of the gain. So from V1 to this terminal B, you have a negative gain, and from here you here from this point to the output of the op amp, the sign should not change, so that the overall sign from V1 to the output of the op amp remains negative. So B has to be positive terminal. So this is how you need. So for op amp 1, B is the positive terminal and A is the negative terminal. Now, similarly for op amp 2, since this is a negative feedback configuration, and this op amp is in inverting amplifier configuration, so you know that the negative inverting amplifier configuration, the feedback is from output to the negative terminal of the op amp. So for op amp 2, the A is the negative terminal and B is the positive terminal. So having found it out, the other thing that you needed to find was the gain. So for gain, again, both the op amps will have a virtual ground. So the terminal A of op amp 2 will be at V2, and terminal B of op amp 1 will be at V1. Now the current I1 that is flowing from V naught to V2 is V naught minus V2 by 2 kilo ohms, and same current flows through this 8 kilo ohm resistor also. So at the output of this 8 kilo ohm resistor, you have V2 minus 8 times I1, and now this voltage, from this voltage to V1, you have this 1 kilo ohm resistor divider, and that will be basically an attenuation of half. So considering that, this voltage divided by 2, so this complete voltage divided by 2 will give you V1. Now, if you rearrange this equation in terms of by putting V naught at one side and V1 and V2 at other side, so you get value of alpha as minus 0.5 and value of beta as 1.25. Any doubt in this? Okay, so if there is no doubt, so this was it about from this session. Thank you for attending.